So this morning, Frank started telling me a little bit about group theory, and I was trying to pick a topic for a basic course in category theory. I thought, okay, what's a topic that I hope that people here will know something about? And I realized, oh, I know something that they're guaranteed to know something about because they'll be worked on it directly before mine. So basically, when Frank said that what he's going to be talking about is sort of just a little corner of some of the things that Bob sketched out at the beginning of his lectures, I'm going to sort of do a little corner of a little corner. So the goal of this course is basically dual. One is to introduce you to the basics of category theory, but that would be kind of boring if it were just a whole bunch of definitions of lemmas and stuff, and stuff from like abstract algebra and topology, which a lot of us probably don't know too much about. So instead, our goal is going to be eventually trying to get an algebraic characterization of this idea of harmony of the connectives. So this morning there was a question from the audience, like what that could mean when the definition of a connective could be harmonious, and this will be sort of a partial answer to that. So this is the basic outline of the lecture. So today we're just going to talk about the basics of category theory. Next time we're going to talk about what I call behavioral reasoning. That's the way that we have to reason when we can't do sort of element-wise characterizations of the objects of study that we're talking about. The third lecture will be about universal construction. So that's how we define things in category theory. Things like the product that Bob told you about earlier. We'll see how we can do many such constructions, and that they're going to be defined in a behavioral fashion. The fourth day will be about the two-dimensional structure of categories. So set theory is sort of a zero-dimensional or a discrete subject, right? Sets are discrete. And we're going to see that we can use categories in such sets. So we sort of add a dimension, which we'll get to shortly, to do that. And so if we want to study categories themselves behaviorally, we're going to see that we need to sort of add another dimension. So we're going to have this two-dimensional structure that lets us talk about behavior of categories themselves. And then the fifth day, I'm going to talk about dependency, and that's going to be important for interpreting the quantifiers that first we have. So the goal for all of the lectures together will be to get some background in category theory, and then eventually to understand how we can understand the harmony of the connectives of first-order logic from an algebraic perspective. And when I say algebraic, I mean like an equational theory of the category. Okay. So there are lecture notes. This is good for you because it means a lot less writing. I'm at Morehouse. If you search for me, there's another guy named Ed Morehouse who's a well-known actor. I'm not him. As far as I know, he has not written any lecture notes on categorical and semantic group theory. So if you go to my webpage and you scroll down to the section on like lecture notes, the first thing in the list, this is good for you because it means you can like spend more time paying attention and thinking and asking questions. And it's good for me because it helps me organize my thoughts and make sure that I don't do things in an order of dependency that doesn't make sense. But I did spend more time sort of scribbling the notes down and a few with genius than I did editing them. So if you find some mistakes, please just let me know and I'll fix them. And likewise, when I write on the board or when I speak, it's like a lot harder to do it from this side of the room than to watch it from that side. So if I say or write the wrong thing and it's obvious that I just made a slip, just shout out the right thing so no one else is confused. And if you have questions that are like clarifying questions, please don't hesitate to ask. But if you're like sort of cognizant about stuff and you're going to ask me a question like, hey, isn't that just like a monoid in the category of window functors or something like that, then reserve those questions till the coffee break or the afternoon so that we can get through what we're trying to get through. Okay, so before I start in on sort of definitions and lemmas and all that stuff, let me give you a very high-level overview of what we're trying to do here. So, from one perspective, you can think of category theory as reimagining of set theory from a different perspective. Right? So instead of the primitive notions being those of set and membership in a set, Instead, we have the notion of set and function as primitive. But we don't stop there, we generalize again. So we don't assume that the objects of study in category theory are sets, but we just think that they're generic objects, and that will be a term of the art in a moment. And we don't assume that the maps between these objects are functions, that is, functional relations. We just assume that they're arbitrary mappings of some sort, right? And the only thing we assume that they have is something called a composition structure, which I'll elaborate on shortly. But to get the right intuition, you can imagine if you're trying to build something out of Lego bricks, for example, right? The order in which you assemble the various bricks to one another that connect them doesn't, in the end, matter in what you build. It only matters sort of the bricks that you started with and which bricks were connected to which bricks, but not the temporal order in which you assembled them. And that's what I'll mean by a composition structure, but I'll explain more shortly. Okay, so as Bob kind of mentioned this morning, this setup gives us a lot of what's called axiomatic freedom, in that by assuming a lot less, we can apply our system to a lot more things. And so by making fewer assumptions, we can describe more things. That's the motto. But, I mean, we're not stuck in an impoverished meta theory because we can always selectively reintroduce assumptions. For example, the law of the excluded middle or the axiom of choice or something like that, and we can recover the systems that we're familiar with from other settings. But the price we pay for this is that we have to reason in a way that I call behaviorally or externally, and that's in contrast to what I'll call structurally or internally. So in set theory, like, we know what elements of a set are, right? We know which elements are members of which sets. But in category theory, we don't know what our objects of study are. We only know how they behave, how they relate to the other objects in the same category as them. And so that's what I mean by studying behavior. So if you want a slogan, you can think of category theory as being like the sociology of formal systems, where instead of taking our objects of study and like dissecting them and like trying to see how they work by taking apart their brains or something, like we just watch what they do, and then we try to infer, you know, what they must be thinking or doing or whatever based on their behavior. Okay, so that's sort of the 10,000-foot overview of category theory. How about categorical proof theory? So, as you learned a little bit from Frank this morning, right, proof theory is itself some kind of formal system. And it also has this kind of composition structure where if you have some sub-derivations of a proof that you're doing, and you put them together eventually to make the full proof, right, it doesn't matter the order in which you put those derivations together, it just matters in the end how they're sort of connected to each other, right? So the plumbing matters, what's connected to what, but not the order in which the pieces were plumbed together. Okay, so the basic idea that we're going to apply eventually is that we're going to interpret logical propositions as objects in some kind of category, and we're going to interpret derivations or proofs. I use derivations to mean a proof which potentially has some some open assumptions. Those will be the arrows between the objects. Okay, and the motivation, as I mentioned already, is we want to discover some kind of algebraic basis for connective harmony. This marker is leaking all over my hand. Okay. So, any questions before we get started properly? Okay. So, we have to start with the sort of founding definition. This is category theory, so we have to know what a category is. So a category which I'll call C. So my notational convention is when I'm making like variables that range over categories, I'll use this blackboard bold notation. So that's the blackboard bold C. It's just referring to an arbitrary category. And it has some stuff. The first stuff it has is data. data as is an object collection. And we'll call this C sub 0. And the sub 0 you should think of as like the zero-dimensional part of it. So the objects are like the points, and that's the zero-dimensional bit. Right? And we write A colon C to mean that A is in the collection C0. Okay? Next, we have a collection of what are called morphisms, or arrows. That is C sub 1. And we write F double colon C to mean that F is in the arrow collection. Okay?
So 0 and 1 as descriptions mean that 1 is the object.
Yeah, so I hope that I haven't made the slip and used the word set yet, because I can't, but eventually we will. So it's just to distinguish two separate collections, right? One is the collections we're calling objects, and you should think of them as zero-dimensional points. The other collection we're calling morphisms or arrows, and you should think of them as one-dimensional things that we'll talk about. Okay, so morphisms are classified by their boundaries. So what I mean is that if, so we write this, we write C, A, B, this, to refer to the collection, okay, collection of C arrows, such that the domain, oh, I didn't talk about the domain. Okay. Okay. Pause that for a second. We now have two boundary functions. These are domain, which I will write boundary negative, and codomain, boundary positive. Okay. And now, okay, I won't erase this, but so arrows are classified by their boundaries. So what that means is we write in the category C from A to B to mean the collection of arrows in C such that the domain of the arrow is A and the codomain of the arrow B, and now I need to do this. Okay, so that should probably actually go under that. And this collection is called HOM, right? So it's just a sub-collection of the collection of all the morphisms, namely the one whose domains are A and whose domains or codomains are B. Okay, so far? Question?
So arrows could have domain, codomain not in this category, not in C0.
The boundary functions go from arrows to objects. Of the same category, right? So you pick an arrow in C1 and you ask what is its domain, and that is an object in C0. You ask what is its codomain, and that is a potentially different but possibly the same object in C0.
So
Sorry?
So the arrows in C1, they always have domain, codomain in C0 or any other?
Yes, the boundary of an arrow in a particular category is a pair of objects from the same category.
Does that notation mean that between two objects there can be more than one arrow?
Yes, there can be many arrows. Okay. let me continue, and then we'll get to examples and what can and can't happen. Okay, yes?
So this is called Tom. What is this?
This is the collection of arrows whose domain is A and whose codomain is B. It's called the HOM from A to B, and it's just a historical term. You can imagine that it probably comes from homomorphism or something like that. Okay, let's continue. We got boundary functions, we got this. Okay, then we have identity functions. Identity arrow. And these are written id, right? And they take objects to arrows. And they have the property that id of an object A is an arrow in the HOM set from A, I use that word, the HOM collection from A to A, right? So the domain of the identity arrow is that same object, and the codomain is also that same object. Okay, and then finally, we have arrow composition. And this is a partial function on arrows, right? So it's best to write it like this. So if F is an arrow, I should also say, before I do this, a notational shorthand is if it's clear which category we're talking about, then we will just drop this C, and we will instead write this as A arrow B, so without the C, without the name of the category. If it's clear from the context which category we're talking about, then we don't have to keep naming it again and again. So the reason I bring this up is that if F is an arrow from A to B, arrow from B to C, then we have F composed, note this dot, infix dot. It's hard to write so well. G, which is an arrow from A to C. So if we want to be careful about this, we take, right, these two arrows have, the composition is defined on them, just in case the codomain of the first is equal to the domain of the second, in which case they have a composite, and that composite has a domain that's the same as the domain of the first, and a codomain that's the same as the codomain of the second. Yes?
This normally would have G dot F. So this
Just wait, okay? I'll get there. Don't give me notational flack yet.
Is ID home from A to A, home from A to A?
It's an element of the HOM from A to A, so it's in that collection. It's a distinguished arrow in that HOM collection. Yes?
What's the difference between an arrow and a morphism?
It's exactly the same thing. The technical word is morphism. I'll say arrow most of the time to be informal because it's also shorter to write, so I'll write it that way. Yes?
The operation which maps an object with an identity or which maps these arrows to the composition, can that be defined on a case-by-case basis, or is it sometimes uniform?
This is the data you must provide in order to have defined a category. And we're not done yet because there's still some more stuff you have to define. But so far you have to have defined at least this much stuff. Yes?
The column after ID of A, colon C, A, arrow A, is that the same column on the left side?
Yeah, so I kind of snuck that in a little bit. I was hoping you wouldn't bring it up. But okay, we're going to see that this is some kind of collection, and we're going to ask what kind of collection. This is going to be a member of that collection. But if you really, you can just think of it as, well, okay, put the epsilon in if you want. Okay. Okay, I'm going to continue. Okay, so that's the data. But now there's also some logs. So I wrote data there, so now I write logs. And so the first law is the left unit law of composition. I'll say of composition, but not rated. And this says, for arrow at A, B, right? So I'm not naming the category, whatever the category is C so far, right? The identity arrow on A followed by F is equal to F. Right? So this is just saying that the identity arrow is a left unit of composition so far, or a pre-unit of composition. Next we have the right, one of these. So again, we have the same arrow. Then if I compose that arrow with the identity arrow on the object B, and I again get that same arrow back. And finally, we have the associated law of composition, which says that if we have three arrows, this, right, then if I first compose the first two, and compose the result with the third, it's the same thing as if I took the first one and composed it with the result of composing the second and third one. Right? So it's just what you would imagine. It's this thing that I told you about before with the Legos. It doesn't matter if you first put the little Lego head on the little Lego torso, and then connect the little Lego legs to make the Lego man, or if you put them together in the other order, you end up with a little Lego man either way. Okay? Okay. So it will get easier. I know this seems a little bit cumbersome, but it's because, when you want to axiomatize something, you have to be a little careful. Okay. So to ease the sort of overhead of terminology and notation, I'm going to add a couple conventions. Right? So we'll say, okay, so that's the end of the definition. Wrong thing to anyway. So arrows F and G are composable. That's a term. If the codomain of F is the domain of G. Okay? So that just saves me the trouble of having to name that object at which they meet. Similarly, we'll say that they are parallel if they have the same boundary. So, slightly fancier name is so I'm saying for I ranging over minus and plus, they have the same domain and the same codomain. That's what makes them parallel. And yes, so if the domains are the same as each other, and the codomains are the same as each other, but not necessarily the domain is the codomain. Okay, so we just did parallel. We have anti-parallel. RL. Okay, so the way we can say this is if they're composable both ways. So that implies in particular that the domain of one is the codomain of the other. And then 2 more, and then I promise I'm done with terminology for a while. And endomorphism. Is a self composable arrow. So that means in particular its domain is equal to its codomain. And finally, path is serially composable list of arrows. So what I mean by that is it's a list of arrows, and each one has a codomain that is equal to the domain of the following one in the list until you get to the end, in which case the condition no longer applies. Okay, so all of this is so that we can talk about arrows, configurations of arrows, without having to name all the objects that are involved if we don't care about the identity of those objects, if we only care about the relationship between the arrows. Okay, I promise you, it becomes natural seeming quickly. Okay, so whoever it was that wanted me to write composition the other way, we write G circle F, F dot G. And the idea is, right, so typically when we're working sort of abstractly or in a point-free style, it's kind of natural just to say the first thing first, and being in a culture that writes from left to right, it kind of makes sense to do that here too. That says you do F, then you do G. But because many times morphisms and categories are some kind of functions, and when we apply a function to an argument, we write the function on the left of the argument. When we have a composition of such things, it kind of makes sense to put the first thing on the right because then it's closest to the argument. So these two things, from my point of view, are totally interchangeable. I generally prefer this one unless we're applying something to an argument, in which case we use this. Okay, and then occasionally we'll write the name of an object to refer to the identity arrow on that object. Okay, so technically this is ambiguous, right? Because we can't tell if I write A if it's the object A or the identity arrow on A. But in some contexts, only one of these is possible. In particular, many times only an arrow is possible. So just for concision, we'll sometimes it typically it would come up until the third lecture or so. Okay, so this presentation might seem cumbersome, or it might not, I don't know, it depends on your background. If it does, let me try to give you sort of the idea that this is trying to get at in a very precise axiomatic way. And that idea is, whenever we have a composable configuration of things, so in the illustrating example, they were Legos, but here they're going to be arrows in a category, right? That there's exactly one way to take that configuration of things and combine it into a composite thing, right? So an alternate axiomatization of categories, which I'm not going to go through because it's even more complicated than this, but it's much closer to the actual intuition of what's going on, is what's called an unbiased presentation. And in that setting, like for every path of arrows that you can form, they have a unique composite, right? So that's the idea. Every configuration has a unique composite. So if the path has length 0, if there's no arrows in the path, then that's what we've been calling an identity arrow on the object at which that 0 length path is based. Right? If you want a path of length 1, that's 1 arrow. Right? If you want to just compose 1 arrow with nothing, with itself, or however you want to think about it, right? Then that's just the identity function acting on that arrow, that arrow is its own unary composite. And then the associative law guarantees us that if we have a path of length greater than 2, then any order in which we put the arrows together to form the eventual composite will end up with the same final result. Right? So that the big idea is that you have this associative compositional structure. And that's the idea I want to get across. The sort of details of the axiomatization are less important. Okay. But there is another presentation of this, which is also quite intuitive. And that is the graphical language of diagrams. So Bob started talking about these a bit in his lecture this morning. But the idea is that instead of writing out, here's a list of arrows, here's their domains and codomains, or here's their composability conditions, we can just draw a little picture, and the picture is worth, if not 1,000, at least a couple dozen words oftentimes. So we have diagrams. So an example is, right, if we want F, and it's composable with an arrow G, then we can just draw it like this. Like this tells us all we need to know, that F and G are composable, and it tells us the domains and codomains of the arrows involved. Okay, but we can convey more information still in what's called a commutative diagram. And the idea here is that it's such a picture in which any parallel path of arrows drawn in the picture has the same composite. Right? So this is what Bob was trying to tell you this morning, but it's easiest illustrated by an example. So if I have A, B, and C again, I have that, I have G again. Now, part of the data of a category, which is generated by now, is that there's always the composite morphism, right? For every 2 morphisms that share a boundary point, which is the codomain of one and the domain of the next, then we know that there is a morphism F composes G. And diagrammatically, this is saying that the arrow F followed by the arrow G is equal to, as an arrow, right, in sort of algebraic theory of arrows, the arrow F composes G. Does that make sense? Okay. I mean, this is just a triviality based on the definition of the category. But we can use this to good effect. So one thing we can do is, say we have 2 arrows that are equal, G1 and G2. Now, if we take an arrow and precompose it here, right, then this diagram is telling us that F followed by G1 is equal to F followed by G2. So this phenomenon is called whiskering. And it's saying basically that the arrow equality is a congruence with respect to arrow composition. And you can do this also on the other side if you have an arrow here. H. Then if we ignore F for a second, it's saying that G1 followed by H is G2 followed by H. And furthermore, you can put the whole thing together to get the 2 paths from A to D that go around the back here. Okay. And another thing we can express using this graphical language of diagrams is what's called pasting. Oh, and I should mention that this terminology, hopefully it's obvious, but the idea, right, is these look like little whiskers coming off of the commuting diagram. You have some commuting diagram here, and you have some arrows going into and coming out of it, which look like whiskers on a cat or something. So the idea behind pasting is expressing the fact that morphism equality is transitive. And so this is equality. And the idea is that if you have 2 diagrams and they share a common edge, then you can take those diagrams and glue them together along that common edge, and you get a new diagram with new paths that must commute. Okay. By example, remember the left unit law for composition says that if I do the identity on A and follow it with F, then it's equal to F. Right? This is just the left unit law for composition. Now, ignoring that triangle for a second, I can also do F first here to get to B, and then do the identity on B. And this bottom triangle is the right unit law of composition. Right? But now they share this common edge, F, so we paste the two diagrams together, and now we get a new piece of information, which is not surprising, but it's telling us that the identity on A followed by F is equal to F followed by the identity on B. Right? So we can take diagrams and paste them together. And now let's sort of combine whiskering and pasting, and we can get the laws of from the definition of the diagram all in two pictures, which is kind of cool. So we have A, B, C, F, G. Then we know we have here F followed by G, right? That's just the composition triangle. We can whisker this guy by H. And now we have two paths that are equal going from A to D. Okay, we can ignore this triangle for a second and put here the composition of G by H and whisker it by F, and now we have another path from A to D, or another diagram, which is equating two paths. Now, those two diagrams share this zigzag path, FGH, right? So we can glue them together along that path, and now we have the composite diagram that says that F followed by G followed by H is F followed by G followed by H, and that's the associative law in the composition in one diagram. So these two diagrams are basically all the laws from the definition of the category. Yes?
The string A to C, if there is another piece going from A to C which is not equal to this composition, we usually don't draw such morphism from the
Yeah.
we can.
So there's different conventions, right? It kind of depends on what you're doing. So one convention you can have is if you have two morphisms that are parallel but not necessarily equal, right? So this is F1 and F2, say. One thing we can do is like puncture it, right? Draw some kind of hole here to indicate that this diagram does not commute. In other circumstances, when you draw diagrams, maybe you're not expecting them to commute. So for example, when we start talking about the two-dimensional structure of categories, we're going to have some things that are like edges between edges, but we're not saying that the diagram commutes. So depending on the circumstances, either that nothing in the region bounded by the paths means that the diagram commutes, or it just means nothing, and you have to be told explicitly whether the diagram commutes or not. But so far, like here, I've been just assuming that the enclosed region means that the diagram commutes. Yes?
To helping alternativity and basing, you require also one of the data to define a category, and put an explanation of arrows and objects and all of these.
Well, so there, I mean, you get an equational theory of parallel arrows, right, based on what arrows you assume are equal going in, and then what you find out about them based on the laws. Right? So, for example, you know that.
It's derived from.
Yeah. Okay. So we've spent kind of a long time talking about the nuts and bolts of representing categories. Let's meet some categories. Okay, so whenever we meet something new and unfamiliar, it's best to start simple. So let's draw a diagram of the simplest possible category that we could have. Okay, and we're done. So
Yeah.
there don't have to be any objects, right? There's no axiom that says there need to be objects, so there can be no objects. If there were objects, there would have to be at least identity arrows, but, you know, we do that. So the empty category, this is, I'll call this 0 with this blackboard bold convention, which, sorry, is probably a little hard to read, but that's a 0. And it has no objects and no arrows. Okay, so let's be slightly less trivial. Let's introduce an object. So we'll call this object star. Okay, once we have an object, we know we're required to have the identity arrow on it. Okay, so we have here a star. But we're not required to have any more data, right? Because we can just say that the composition of, but in fact it's required that the composition of id star with itself is itself, right? So we're good with that. The associativity is okay. So this is a complete characterization of a particular category. And this is a single category, which I'll call blackboard 1. Okay, so we can sort of generalize this pattern by having more objects. One thing I should have said when I was talking about diagrams is sometimes when I make the diagrams, I won't bother to name the objects. I'll just put a dot, and a dot just means an anonymous object. It's like an underscoring tag bit. Right? So we can have more objects, but for each one, we're required to have little identities, but we're not required to have anything else, right? So, but we can do this for any number of objects, and these are called discrete categories. And in fact, any set can be thought of as a discrete category. Okay? So the objects of the category just become the elements of the set. And the arrows of the category are the required identities, but then there's nothing else. Okay? And so composition is trivial. So let's be slightly less discrete and see if we can make a slightly more complicated category. So as Bob told you this morning, right, there's this idea of a preordered set, which is a set with a reflexive and transitive binary relation, right? And for any preordered set, we'll call it P, so that's the set P, with the relation all less than or equal to, we can define we have pre-ordered category. Okay, so I have to tell you what are its objects. Oh, I should name this thing, so I'll name it Blackboard bold P. Okay. So the object collection of this thing is just defined to be the set underlying the preordered. The arrows so in the HOM of P from X to Y, we have two possibilities. Either a singleton set, whose element we'll call X is less than or equal to Y, if indeed X is less than or equal to Y according to the relation on the preorder, right? And empty otherwise. So in other words, the HOMs are either singletons if the relation holds between the domain and codomain, or they're empty it doesn't. And I have to tell you what are the identities. So in an element x is just defined to be the arrow called x is less than or equal to x. And the composition I have x is less than or equal to y with a morphism. Now I compose that with a morphism y is less than or equal to z. This is a z, by the way. Then this is equal to the morphism called x is less than or equal to z. Okay? And we know that these hold in the category because the preordered set, the relation here, has to be reflexive and transitive, right? So this is just witnessing the reflexivity of the relation, and this is just witnessing the transitivity of the relation. Okay? So in a preordered category, a few things happen. First of all, as I said, every column is either a singleton or it's empty. Second of all, the unit and associative laws of composition are automatically satisfied, right? Because in either an empty set or a singleton set, all of the elements are equal to each other, trivially. And so that implies that every diagram in a preordered category has to commute. Okay, so let's try to think of a preordered category that's not discrete, right? As we're sort of building up our library of examples. Preordered category not discrete. Okay. Well, if it had no objects, then it would already be discrete, right? Trivially. If it has one object and the columns are singletons or empty, but we know that the identity lives in the column from an object to itself, then that would be discrete. So we have to add a second object, right? But we can't just have the identities on those two objects because that would be discrete. So we have to add another arrow from one object to the other. Right? And I should have said this before, but generally we need to draw in the identities or the composite arrows in diagrams because we can always infer their existence from the laws of the category, from the structure. Okay, so this thing is the simplest possible category, which is not discrete, but is a preorder. Right? And this thing is called the integral category. And we write it with this blackboard bold I for integral, which looks like Roman numerals. Sorry about that. Okay, and it turns out that this is very important when we start to talk about the higher dimensional structure of categories. Okay, so keep this in mind. Question or comment?
So what makes it not discrete?
So the discrete categories were a set considered as a category. So we had the objects would be like the elements of the set, and then the only arrows in the category would be the required identities, the little loops. Right? So here we have an arrow that's not a loop, that's not an identity, and therefore it's not discrete. Okay. Continuing with our little library of examples. So, I don't think Bob talked about this morning, but as you may know from somewhere else, or if not, I'm about to tell you, a monoid is a set together with an associative binary operation with a neutral element. So in other words, we have something that looks like this. So this is a set. This is an associative binary operation. This is an element that is neutral with respect to this operation. Right? So think, for example, the natural numbers under addition. Yeah, so natural numbers, addition, 0. Right? So if we have a monoid, we can think of it as a monoid category. So I should also give this a name. Call it Blackboard Voltage M. Good. And now I have to tell you its structure. So it has objects. The object collection is defined to be the singleton set consisting of an anonymous object, which I'll again call star, like in the case of the singleton category. Okay, so I have to tell you about the arrows. So, and the home from star to star is defined to be, well, it's whatever the object set of the monoid was. Right? So in this case, it would be like the natural numbers. And the identities, well, there's only one, right? Because there's only one object. So the identity that's defined to be the neutral element in the monoid. And the composition x composed with y is defined to be just x. So the binary operation of the monoid, which is typically called multiplication generically, although it's not, as in this example, actually multiplication, right? But it's just whatever that operation is acting on those two elements. Okay. And so we know that the unit and associative laws of composition for a category are satisfied exactly because in a monoid, this operation is associative and unital with this unit. Okay. So the category laws are satisfied exactly because the monoid laws are required. So one way to think about this is you can imagine sort of the anonymous object sitting here hanging out. And for each object in the monoid, we have a little loop on this object. Okay. And then when we want to compose arrows in the category, we just ask the monoid operation what the result of applying the operation to those elements is, and that is the result of composing the arrows in the category. Right? So let's try to think of a simple monoid category that's not discrete. Okay? So we know we have to have this object because that's just part of the definition. Right? If we had no arrows except for the identity, it would be discrete. Right? So I'm not going to draw the identity, but we know it's there. So let's postulate a new arrow, which we'll call S. Okay? Now, since we've postulated that S is in the home collection from star to star, now we have a bunch of other arrows that have to be in there. They have no choice. Namely, we have S composed with S, S composed with S composed with S, and so on. They have to be in there. So the question is, what should they be? And there's not a single choice. There's different possibilities. But one possibility is if we impose no laws at all, right, that these are all distinct arrows, then we get this whole collection of arrows. We get epsilon, we get s, we get s composed with s composed with s composed with s, and in general s sort of to the nth power, which is s composed with itself n times. Right? And this structure, if we made these choice, this turns out to be just like this kind of natural numbers with addition of 0, because basically we're counting how many times we go around s, right? And if we compose going around s 2 times and going around s 3 times, then we go around s 5 times. So it's just like adding 2 and 3. And epsilon becomes 0, right, going around s 0 times. So this category turns out to be, well, we haven't talked about it yet, but we'll soon see that it's isomorphic to the monoid of natural numbers under addition. Okay. So, question?
What distinguishes S from the identity arrow? Because they're both going from star to star.
Yeah, so remember our little goal here, I didn't write it down, I guess I should have, was to define a simple monoid category that's not discrete. So if S were the identity, right, and if that were the only arrow in the category, then that category would be discrete.
Oh, so there can only be one identity per object?
So that turns out to be the case, but it's something that it's a little level.
If we force s composed s to be equal to s, then
Yeah, that's a different possibility.
Will we force it to be the identity?
You could, well, yes, if you can force it to be the identity, then you get like the natural number 1 or 2. That's the monoid thing. Someone shout out if that's not
Yes.
Okay. Good. Okay. So
Sorry, what's the question?
the question was, what happens if we force s composed s to be epsilon, the identity?
Well, that's just reflection. It doesn't have to be.
It doesn't have to be, right? So as I said, like here, there's not a single simplest monoid category that's not discrete. There's a number of choices we can make, and those choices have to do with what laws we want to hold between the various compositions with itself. Okay, this was just meant to be a little example. Don't get too caught up in it. Yes.
So what did you do differently in defining this one than on the singleton? Just the one circle, I mean the one arrow.
So, okay, so if there had been no generator S, if the only morphism in the Hom collection from star to star had been epsilon, namely the identity on star, then that category would be discrete. In fact, it would be the singleton category. So this has been maybe, depending on your background, either this is just like simple finger exercises or it's like crazy talk. And if it's the latter, let's bring this down to earth a little bit and sort of remind ourselves where we're going. So as I said sort of over here, when I was sketching what I kind of want to try to convey to you in these lectures, I want to talk about semantics for proof theory, right? So we want to make categories that have something to do with proof theory. And in particular, we want to have some way of sending propositions. So this is just a sketch because we don't yet have enough information to sort of explain this, but we want to have categories that have something to do with propositions and proofs. Then we want their objects to interpret propositions and eventually what are called propositional contexts, which we'll get to soon. Okay? So in other words, if we have a proposition A, right, then we're going to have to find some kind of interpretation function which sends the interpretation of a proposition A to be an object in some category eventually. Right? This is way underspecified so far, but I'm just giving you the idea. And likewise, if we have some propositional context, we're also going to interpret that as an object in some category. Right? So these double brackets are semantic brackets or Scott brackets, and it just means the interpretation of. Okay, so how about the arrows? Well, we want them to interpret derivations. And by derivation, I mean like the proofs that Frank was doing this morning, but I don't assume that the context of assumptions is empty. So it might be a proof with some undischarged assumptions. Right? So I'm using the word derivation for that. I'm just not sure if that's Frank's convention. So schematically what we have is that if we have some kind of derivation, which I guess Frank wrote like this, right? Here's some context of assumptions, here's some derivation, here's the conclusion A, then we interpret this whole thing as an arrow from the interpretation of the assumptions to the interpretation of the result. Okay, and I haven't said how to do this yet. I'm just, this is where we're going. This is not how we get there. Okay. Identities. So these are going to be identity derivations. What are those? Well, okay, say I have a proposition A, right? And now I perform no inference rules. And now I have, well, sort of a trivial derivation whose conclusion is the proposition A, and whose like set of assumptions, propositional context as I call it, is the singleton set containing exactly the proposition A. Right? So you can think of this as some kind of derivation of A from itself. Okay. And then finally, compositions, I won't talk about yet because we don't have enough machinery to yet talk about how to compose derivations and interpret those. Okay, so, I've got like 15 minutes, is that it? Someone stop me when I'm done. So far we've talked about some structured sets as categories, right? We had the category of, we had discrete categories, which were totally unstructured sets, i.e. just sets. We had pre-ordered categories, which were like pre-ordered sets, and we had monoid categories, which were sets with this binary associative mutable operation on them. But we also have categories of structured sets. So those were, so what we've just been talking about for the last little while was structured sets as categories. And now, I want to talk about, in contrast, categories of structured sets. Okay. So if there's no structure at all, then we just get the category of sets. And so this is called, and we'll adopt this convention, and we'll use this this is called like small caps thing. If I'm naming a category like as a proper noun here, this is the category of sets and functions. I have to tell you all this stuff, whether it's objects, well, they're just sets, whether it's arrows, well, they're just functions, whether it's identities, they're the identity functions, right? And the x dot x. What is composition? F compose G is defined to be x dot G of F, which is function composition. And then we have, you can check, or you hopefully already know, that function composition is associative and unital, right? Or the identity function. Okay, so the next structured set as category we did was the pre-ordered sets, but we also have a category which I'll call P, R, E, O, R, D, again with this small cap convention, and this is category of pre-ordered sets. So I have to tell you whether it's objects. No surprise, they're the pre-ordered sets. Arrows. So there have to be some kind of function because your sets are sets, and they have to preserve the order. Okay, so these things are called typically monotone maps. But they're order-preserving functions. Okay, I can tell you what are the identities. But they're just the identity functions. I have to tell you what is the composition, but that's just function composition. And then you have to check that the identity function is order preserving and that the composition order preserving function is order preserving, but that's pretty easy. Okay. So to sort of finish off our little menagerie here of simple categories, we have the category of monoids. Okay, so this is probably pretty obvious by now, but what should be its objects? Monoids, yep. Arrows. Okay, so here, depending on whether you've seen this before, here there's this notion of monoid homomorphism, right? So let me explain that. the idea is that if we have a function f in mod from m star epsilon to n, so star prime epsilon prime, right? This is defined to be a function f from m to n. Right, so this is in set. I should see that. Such that, and it has to now preserve, this time, the monoid structure. Right? So in particular, we have, if we first multiply two elements and then send them over to f, it's the same thing as sending them over and then multiplying them once they get there. And similarly, if we send over the unit, then it's just the unit. Okay. And then you have to check that identity functions, identity morphisms are identity functions, and composition of morphisms is function composition, so you just have to check that those things preserve the monoid structure. Okay, so this is like sort of, a little menagerie of structured sets as categories and categories of structured sets. But what have we seen here, right? We've seen that these structured sets, these categories of structured sets are actually categories of categories because the things in them we saw could be conceived as categories, right? So sort of sneakily, I should be done.
5 more minutes.
Okay. Let me just say. This pen writes really well, but erases really poorly. We've just seen we can form categories of categories, right? But when we have these things, then we ask, like, what are the morphisms between them? Right? So now we have to ask ourselves, what is a morphism between categories? And this brings us to the idea of a function. So if we have categories C, D, functor F, and C to D is comprised of function on objects, f sub 0, right, and it goes from C sub 0 to D sub 0, and a function on arrows, so that's f sub 1, then from C sub 1 D sub 1. And now we have to have some coherence data here between them. So the first is mean by that is that if we have an arrow F and C into B, then that gets sent to some arrow in D from F 0A to F 0B, right? And this is F1. So in other words, the functions on arrows respect the boundary relation on the arrows, like between the two categories. Right? So if you take the domain and codomain of the image of an arrow, it's the image of the corresponding object. And there's one more division. And that's respect for composition structure. And the easiest way to explain this is if we have an identity arrow, then that gets mapped by the functor to, well, it has to be some arrow from F of F. Okay, I'm going to stop writing the subscripts because they're, again, obvious. Based on the dimension, right? But this has to be some arrow from F of A to F of A, because that's where the object part sends A. And now the question is, which one? Well, if it's respecting the composition structure, it could send the identity to the identity. And lastly, if I have two composable arrows here, their composition, we know what where the two arrows have to go. They go from F of A to F of B, so that's F, the functor F applied to the arrow F. And likewise here, we have the functor F applied to the arrow G. And then the question is, where should the functor F apply to the composite F followed by G? And respect for composition structure says that it should go here. Namely, that this diagram should commute. So if you apply the functor and then compose, it's the same as if you compose and then apply the functor. Okay, and then I'll stop there. And I'll take questions. Any questions? Sorry? Well, what do you mean exactly? Well, okay, so we're going to see the very next thing, right? That just, although we can form categories of categories, we can't form a category of all categories for the same foundational reason that we can't form a set of all sets, right? Because then you can get some kind of paradox. So I'm not exactly sure what you mean by that, but if you mean like the objects of the category depend somehow on some property of some. Okay, so we will soon see that we can do what are called universal constructions in categories, so we can form things like products and exponentials, as Bob talked about earlier. But I think that that's not what we mean, so maybe we can talk about it. Anything else?
What about category of sets? Because the same question applies when we say that the category objects are sets and there's no physical expansion.
Yeah.
Question is how many sets there are.
Right, so actually that's the next topic, but I was far too ambitious in terms of my planning here. So we will have exactly the same foundational questions that come up in sets, right? So we can make a category of some categories, some that we choose. But we have to make, well, we should be careful that that category is not itself one of these categories. So maybe this is the impredicativity tension, because otherwise then you can get some kind of like foundational paradox, like a Russell's paradox type thing. So there's different ways to deal with this. There's, you can stratify categories by size. There's something called like universes. But in general, we're only going to care about sort of the smallest level in this hierarchy. So we're going to have categories whose object collection and morphism collection are both sets, right? So they have some cardinality, basically. And those are going to be called small categories. But we're going to have to observe that the category of small categories is not itself a small category. And then we have a couple other similar notions of size that I'll talk about next time. But basically, we stratify things by size. Okay, so let's have coffee or whatever, and I'll be around if anyone wants to ask questions or